Hello everyone, welcome to lecture 9 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be discussing about electromagnetic waves in materials. So here is the lecture outline. We will briefly discuss about Maxwell's equation in free space, then we will see how it changes in a source free medium and then in a conductive medium. We will also discuss about the boundary conditions, power and intensity, energy and power density, momentum, and then we will look into electromagnetic waves in dielectric medium such as linear, non-dispersive, homogeneous and isotropic medium, also in nonlinear, dispersive, inhomogeneous or anisotropic medium. So, as discussed in previous lectures, an electromagnetic wave can be described by two related vector fields that are basically function of position and time. So, what are those? The electric field E, function of r and t. Similarly, you have magnetic field H, which is also function of r, t. So, r basically represents x, y, z, okay, coordinates. So, there are basically 6 scalar functions of position and time that are basically required to describe light in free space. So, 3 from here, 3 from here. Fortunately, these 6 functions are basically interrelated, since they must satisfy the celebrated coupled partial differential equations, which we all know as Maxwell's equations. So, this is how the electric and the magnetic field vectors in free space looks like. They will be interrelated with Maxwell's equations. So, you all know that there are 2 divergence equations and there are 2 curl equations. Okay. So, in free space, divergence of E is 0, divergence of H is 0, and this is the curl equation. So, it shows curl of E equals minus mu naught dou H by dou T, and curl of H equals epsilon naught dou E by dou T. So, epsilon naught and mu naught, you know, this is the vacuum permittivity and permeability, and you know the standard values, right. Now, how things change in a source free medium. So, if you consider a medium which is devoid of free electric charges and current, you basically bring in 2 additional vector fields. One is called the electric flux density or the electric displacement, denoted by D, capital D. That is also a function of position and time, and then you have magnetic flux density B, which is also position of function of position and time. So, now we have 4 fields E, H, D and B, right, electric magnetic fields, and then you have electric flux density and magnetic flux density, right. So, they are related by Maxwell's equation in a source free medium in this particular form. So, now we change the divergence equations to divergence of D equals 0, divergence of B equals 0, and the curl equations look like this: curl of E equals minus dot B dot T, curl of H equals dot D dot T. Now, what is D? This is basically where your medium is getting into picture. So, you have epsilon naught E, that is coming from the vacuum part, okay. This was there in the earlier case as well, but P tells you about the polarization in a particular medium, okay. So, this is where the medium gets into the equations. Similarly, for the case of magnetic flux density, this is for the free space, but then you have an additional term, magnetization, coming into picture for the medium. Now, if you want to see how the equations work for a conductive medium such as metal, which has got lot of free electric charges, okay. So, they are free to roam, the charges are free to roam. That means there will be an associated current density J, okay. So, in that case you need to add that current density term to the right hand side of the curl equation. So, your fourth equation changes like this: curl of H equals J plus dot D dot T, right. And the relationship between the electric flux density D and the electric field, as I mentioned, depends on the medium properties, which are characterized by the polarization density P. Similarly, in a dielectric medium, the polarization density is nothing but a macroscopic sum of all the electric dipole moments which are induced by this external electric field in the medium. And if you think of the other equation, the magnetic flux density equation, you will see that the magnetic flux density B is dependent on the magnetic field H, also on the magnetization density M, which is very similar to the polarization density. So, this happens in a medium in the presence of a external magnetic field. So, your equations are basically this, right. So, this is where your magnetic properties of the medium and the electric properties of the medium gets into the Maxwell's equation. And if you want to retrieve the equation for the free space, you can simply put the polarization and magnetization to 0. In that case, your D simply becomes epsilon naught E and B becomes mu naught H. So, you retrieve the same equation of free space. So, this kind of equations, when you are relating D with P and then B with M, that is where the connection between the medium and the electromagnetic waves in getting established. Now, let us look into the boundary conditions. So, in the case of homogeneous medium, we understood that all the components of the fields like E, H, D and B, they are continuous functions of position. Now, at the boundary between two dielectric medium, so we have discussed this briefly in the previous lecture as well. Say you have medium 1 and medium 2, and we are considering that in the absence of any free charges or current, what we will see that the tangential component of the electric and the magnetic fields are basically continuous, whereas the normal components of the flux densities, electric flux density or you can say magnetic flux density, both they must be continuous. Now, if you consider a boundary between dielectric medium and a perfect conductor, in that case the tangential component of the electric field vector must vanish, since this one behaves like a perfect mirror, or you can say a perfect mirror is basically made of perfectly conducting material, something like a metal, and there the component of electric field parallel to the surface of the mirror must be 0. So, this requires that at normal incidence the electric fields of the reflected and the incident waves must have equal magnitudes and a phase shift of pi, so that their sum will add up to 0. So, these boundary conditions are an integral part of Maxwell's equation. They are basically used to determine the reflectance and transmittance of waves at various boundaries, and also to find out the propagation of waves in periodic dielectric structures and waveguides. So, it is very important to understand the boundary conditions. Next, we will look into some of the properties of the electromagnetic waves, something like power and intensity. So, when you say the flow of electromagnetic power, it is basically governed by or given by Poynting vector S, which is obtained as a cross product of the electric and the magnetic field, and the direction of the power flow will be orthogonal to both E and H. So, it is something like you take the cross product. So, if you can use your right hand thumb to point, if you take your fingers towards electric field and then you bend it around to the orthogonal direction, you will get the magnetic field and your thumb will be showing the Poynting vector, that is the direction of the power. So, next important parameter is optical intensity, that is nothing but the power flow across a unit area which is normal to the vector S, and that is nothing but the magnitude of the time averaged Poynting vector. So, that is given by this time average of the Poynting vector, and this average is taken over times that are long in comparison with an optical cycle. You can further utilize this vector identity, which is del dot E cross H. So, you are basically taking the divergence of the Poynting vector and you can write it like this: curl of E dot H minus curl of H dot E. Okay. When you combine this with the Maxwell's equation that you have seen for any material, okay, you can obtain del dot S, which is this term, okay, turns out to be minus dot D dot E, half epsilon naught E square plus half mu naught H square minus E dot dot P dot E minus mu naught H dot M dot E. So, as you can see here, the first two terms, this one basically give you the electric energy density, that is per unit volume, and this one gives you the magnetic energy density of the wave, okay. And the third and the fourth term basically give you the power densities, okay. So, this gives you energy density, this gives you power density, this is the electric power density and this is the magnetic power density, okay, for the electric and the magnetic dipoles. So, this equation, also known as Poynting theorem, therefore represents conservation of energy. So, the power flow escaping from the surface of an incremental volume equals the time rate of change of the energy stored inside the volume. Next, we will learn about momentum. So, an electromagnetic wave carries linear momentum, which results in radiation pressure on objects on which the wave is falling, or the wave reflects, or you can say from which the wave reflects or scatters. So, in free space, the linear momentum density calculated per unit volume is a vector, and that looks like this. So, epsilon naught E cross B will be equal to 1 by c square S, S is the Poynting vector, okay. So, this is your linear momentum. Now, if you consider an average momentum in a cylinder of length c and the unit area is this, so it has got a unit area. In that case, the momentum will be S by c square, and then you multiply by length, okay, because the area is 1. So, you get the volume, okay, you get S over c. So, this momentum basically crosses the unit area in a unit time. So, that is how you can interpret this. So, you can say this is the average rate per unit time of momentum flow across a unit area oriented perpendicular to the direction of S, and that value is basically S by c. Now, interestingly, your electromagnetic wave may also carry angular momentum, and that may exert torque on an object, and the average rate of the angular momentum transported by an electromagnetic field will be r cross the time average of the Poynting vector by c, okay. So, these are some important properties of the electromagnetic waves, the parameters that are used. Now, with that we will see how electromagnetic waves behave in a dielectric medium, right. So, it is useful to regard the PE constitutive relation. So, PE is the polarization density and the electric field, okay. So, that arises from a system in which epsilon is the input and P is the output, or you can say the response, okay. So, E is basically function of both position and time, similarly P also, okay. So, you can think of like this. So, there is a medium which has got a dielectric permittivity of epsilon. When electric field falls on that medium, it generates a response or output in the form of P, right. So, a dielectric medium is said to be linear if the vector field P is linearly related to your vector field E, right. In that case, the principle of superposition will apply. The medium is also called non-dispersive if its response is instantaneous. That means, if P at time t is determined only by the electric field at the same time, not from the electric field values which were previously there, right. So, non-dispersiveness is clearly an idealization, since all physical system, no matter how rapidly they may vary or they may respond, they do have a finite response time, isn't it. So, for our sake of simplicity, we will consider non-dispersive, where the response, the electromagnetic response, is instantaneous. The medium is also said to be homogeneous when the relationship between P and E is basically independent of the position R. Okay? And you can call a medium isotropic if the relationship between P and E is independent of the direction of the vector E. That means the material or the medium basically exhibits similar behavior in all direction. So, in that case P and E. So, now we will look into linear, non-dispersive, homogeneous and isotropic medium. Okay? So, this is the first case we will be considering, and this is the simplest one. So, our medium is linear, as I mentioned, non-dispersive, homogeneous and isotropic. So, the vector fields P and E at every position and time parallel and proportional. So, that you can simply write P equals epsilon naught chi E, right. So, chi is a scalar constant which is known as electric susceptibility. Okay. So, linear, non-dispersive, homogeneous and isotropic medium, as you can see here, it can be fully characterized by a single constant which is called chi. So, this is good enough, this one constant is good enough for mapping all the properties, electric properties in this kind of cases. So, you can write the electric flux density D equals epsilon naught E plus P. P can be written as, from this equation, epsilon naught chi E. You take epsilon naught E common, you get 1 plus chi, and that is nothing but epsilon R. And when you take epsilon naught and multiply with epsilon R, you get epsilon. Okay. So, this is the permittivity of the medium, the electric permittivity of the medium. So, as I mentioned, this term is basically epsilon R, that is nothing but epsilon over epsilon naught, that is the relative permittivity, and that is given plus 1 plus chi. Under similar conditions, the magnetic relation can also be written in the form of B equals mu H. So, D equals epsilon E, B can be also written as mu H, where mu will be the magnetic permeability of the medium. Now, in such cases, okay, you can simplify the Maxwell's equation to this form. Okay. So, we are just keeping things simple here. D is epsilon E, B equals mu H. Okay. So, it is apparent that these equations are identical to the form of the free space Maxwell's equation. Only difference here is that epsilon is replacing epsilon naught and mu is replacing mu naught. So, from this you can also write down the wave equation in a medium, that can be written as del square u minus 1 by c square dot square u by dot t square equals 0. Okay. So, here the scalar function URT represents 3 components, okay, Ex, Ey and Ez of the electric field, or the 3 components Hx, Hy and Hz of the magnetic field H. Okay. These are the 3 components. So, either these 3 components or these 3 components, right. So, you can get the wave equation. So, if you see this equation, it has got c, which is basically the speed of light, and you can correlate the speed of light with the permittivity and permeability of the medium using this equation. C equals 1 by square root of mu epsilon, right. So, for non-magnetic medium, if you consider mu and mu naught to be equal, okay, so this goes off. So, whatever you have here is nothing but epsilon R, and you can write this as 1 plus chi. Okay. So, refractive index n can be written as square root of epsilon R or square root of 1 plus chi. Okay. Now, let us see how things change in the case of a inhomogeneous medium. So, if you consider non-magnetic dielectric medium for which one of the properties of linearity, non-dispersiveness, homogeneity and isotropy are not satisfied. So, let us first start with this case, as I mentioned, inhomogeneous medium. So, we are considering a graded index medium. So it is not homogeneous, it is graded index, means the refractive index varies along the direction, along the position. Okay. So otherwise it is linear, dispersive, anisotropic. Okay. So it is just graded index, so it is inhomogeneous. So in that case the simple proportionalities, okay, like P equals epsilon naught chi e and D equals epsilon e, they will remain intact. Just that the coefficients chi and epsilon, they will now become functions of position. So you got to write chi equals chi r, epsilon equals epsilon r, because it is graded index. So along the position the refractive index changes, and this tells you that refractive index is also position dependent. So you should represent it as n function of r. So this is how things look like in this particular scenario, where you have a inhomogeneous but otherwise linear, non-dispersive and isotropic medium, right. So this is basically characterized by a position dependent susceptibility chi r. So for media with gradually varying dielectric properties, that means when your epsilon r varies sufficiently slowly, it can be assumed constant within distances of the order of the wavelength, and in that case the wave equation can be written as del square u minus c square, which is position dependent. You can put this the speed of light in that particular medium, which is position dependent, and then you have dou square u by dou t square equals 0, right. So what is important here to note that because your refractive index n is nr, okay, that means your c r is also nothing but the speed of light in vacuum c naught divided by nr. That means you have a spatially varying speed, okay, and that is all happening because your refractive index is spatially varying. Next, for anisotropic medium, the relationship between the vectors p and e depend on the direction of the electric field, and the requirement that the two vectors in isotropic, the two vectors are parallel, but here they are not parallel, right. So if the medium is linear, non-dispersive and homogeneous, okay, in that case, but it is anisotropic, so each component of P is basically a linear combination of the three components of the electric field. So you can write Pi equals sigma over j epsilon naught chi I j E j. So each component of P, that is Pi, will be dependent on the three components of j. So I and j are basically here 1, 2, 3, that indicates your x, y and z. So the dielectric property of the medium will in this case be, because I and j both are running from 1 to 3, so it is a 3 by 3 area of constants, okay, as you can see here. So you are basically getting a tensor, susceptibility tensor, okay, that is determining the material property. So once you understand how this works, so you can apply the same relation for D and E as well in the case of anisotropic medium. So Di becomes sigma over j epsilon I j E j. That means for j is running from 1 to 3, I is also running from 1 to 3, okay. So your epsilon I j is basically giving you the elements of the electric permittivity tensor, right. So in an anisotropic, but it is a linear, homogeneous and dispersive medium, in that case the permittivity will also have 9 components, okay, and these components are basically coming from the electric susceptibility tensor, right. So if you go back to the previous equation, you will see that E1, okay, is, you can see from this one that Pi equals sigma j, okay, epsilon naught chi I j E j. So all the three components of the electric field will give you each component of polarization. So P1 will be dependent on E1, E2 and E3 via the constant susceptibility constants of chi 11, chi 12 and chi 13. Similarly, P2 will be dependent on E1, E2 and E3 via these are the susceptibility elements chi 21, chi 22 and chi 23. Similarly, P3 will have chi 31, 32 and 33. Now, we will see how things change for the case of dispersive medium. For a dispersive medium, the relation between P and E is dynamic rather than instantaneous. So, you have to now think of time dependence in the case of electric field and the polarization density as well as in the material parameter. This is coming from the material parameter because things do not change instantaneously, right. So, the vector E t may be thought of as an input that basically induces some bound electrons in the atoms of the medium to oscillate, which then collectively give rise to some polarization density vector P t as the output. So, that takes some time, and that is the presence of time delay between the output and the input, and that indicates that the system possesses some memory. So, only when this time is short in comparison to the other times of interest, this response can be regarded as instantaneous, then you do not care. In such cases, you can consider the medium as non-dispersive, right. But if you say that it takes some finite amount of time, so it is a dispersive medium. So, for dispersive medium which are linear, homogeneous and isotropic, the dynamic relationship between P t and E t may be described by a linear differential equation such as that associated with a driven harmonic oscillator, something like this: A1 dou square P dot E square plus A2 dou P dot E plus A3 P equals E. So, this A1, A2, A3 are constants. So, what we have seen that in a dispersive medium, but it is a linear, homogeneous and isotropic, the relationship between P t and E t is basically governed by a dynamic linear system described by an impulse response function epsilon naught chi t, right. That basically corresponds to a frequency dependent susceptibility, which is chi f. You can also think of it in the frequency domain terms, right. So, a linear system approach may be used to investigate any arbitrary linear system which is characterized by its response to an impulse. So, you are basically thinking about impulse response function, right. So, an electric field impulse, if you consider of magnitude delta t, and that is applied at time t equals 0, that will introduce, or you can say induce, a time dependent polarization density of magnitude chi naught epsilon naught, magnitude will be around epsilon naught chi t. So, this chi t is basically a scalar function of time with some finite duration that begins at t equals 0. Now, since the medium is linear, any arbitrary electric field E t then induces a polarization density that is a superposition of the effects of E t prime for all t prime less than equal to t. So, it is covering everything before that time t, so that the polarization density can be expressed as a convolution. So, you can write P t equals epsilon naught integration plus infinity to minus infinity x, or you can say chi t minus t prime E t prime d t prime, right. So, this is how the dielectric medium is completely described by its impulse response function epsilon naught chi t. So, alternatively, a dynamic linear system may be described by its transfer function, which governs the response to harmonic inputs. The response function is a Fourier transform of the impulse response function. In this particular example, the transfer function at frequency f is nothing but epsilon naught chi f, where chi f will be the Fourier transform of this chi t. So, that that is basically becoming a frequency dependent susceptibility. For magnetic media, under similar assumptions, the relationship between the magnetization MT and magnetic field HT will be very similar to the convolutional equation that you have shown here. Now we move to nonlinear medium. For the case of a nonlinear dielectric medium, it is defined as one in which the relation between P and epsilon is nonlinear, in which case the earlier wave equation is not applicable. That means this is not applicable. Okay? Rather, you need to take Maxwell's equation to derive a nonlinear wave equation that electromagnetic waves obey in such a medium. Okay? So, first we have to derive a general wave equation that is valid for homogeneous and isotropic non-magnetic medium. So, operating on the Maxwell's equation, curl of E equals minus mu dou H dot E with the curl operator and using the relation P equals mu naught H and curl of H equals dou D dot E, you can write curl of E equals minus mu naught dou D dou square D dot E square, right. So, you can take, like, basically what you are doing, you are taking curl of this. So, here also you are introducing curl of H, from curl of H you are putting this D, right. So, you have got this one, then you use this particular vector identity, that curl of E is nothing but gradient of divergence of E minus Laplacian of E, and then you have this relation that you already know, D equals epsilon naught E plus P. When you put this together, you get this one. So, you get this the left hand side, okay, that is this part, and this becomes this minus epsilon naught mu naught dou square E dot E square minus mu naught dou square P dot E square. So, if you consider homogeneous and isotropic medium, D equals epsilon E, in that case your divergence of D is 0, that is equivalent to divergence of E becoming 0. So, this part blows off. Okay. So, you are just left with this one. So, you write, you remove the minus from all sides, okay, and then you bring this side, this term on the left side, you will get this. Okay. And one replacement is done here. You can see that epsilon naught mu naught is nothing but 1 over c naught square. C naught is the speed of light in vacuum. So, you can use this equation, and this is the equation in a nonlinear medium, right. So, this ideally this is particularly the equation that is applicable for all homogeneous and isotropic dielectric medium, whether it is linear or non-linear, non-dispersive or dispersive. So, this is the master equation, you can say, right. Now, let us focus on the special case that we want this to be non-linear. Okay. So, if the medium is non-linear, non-dispersive and non-magnetic, the polarization density P can be written as a memory loss nonlinear function of E. Okay. So, you can write P equals psi of E, okay, which is valid at every position and time because it is non-dispersive. So, there is no time dependence, okay, and it is happening everywhere. So, you can take this dependency can be represented like this. This is the simplest case. Say the polarization is dependent up to second power of E. So, you have A1 E plus A2 E square. Okay. So, under this kind of condition, you have to take the partial differential equation. Okay. So, you get nonlinear partial differential equation for the electric field vector E. Okay. So, if you just refer to the previous case, the generalized one, okay, there you put this, and this is how it looks like. Okay. So, P is now psi E. So, this dependency can be anything, so that you put here. So, now because it is nonlinear, the principle of superposition will no longer be applicable because it is a nonlinear nature of this wave equation, and nonlinear magnetic materials can also be described using the similar method. So, most dielectric media are approximately linear unless the optical intensity is substantial, as in the case of focused laser beams, right. So, with that we will Thank you for this lecture. If you have got any queries, you can drop an email at this email address. Thank you.